Hi, I'm Rich, a PhD student from Imperial College. Today I'm going to talk about optimization and compressive testing of additively manufactured stainless steel corrugated shell. I'll divide my presentation into four parts: background, optimization design, experiments, and adjusted FE predictions. Let's move to the first part. Cylindrical shells are widely used in wind turbine tower, aircraft fuselage, and storage tanks. However, the cylindrical shells are known to be sensitive to imperfections. Let's look at this example. We can see that with the increase of the slenderness, the actual resistance decreased drastically with the increased slenderness. Even the imperfection amplitudes are within the manufacturing tolerance. In structure designs, empirical knockdown factors such as the well-known NASA and the Eurocode 3 consider the effect of the imperfections implicitly or explicitly. Another approach is the introduction of the stiffeners. The stiffeners can somewhat reduce the imperfection sensitivity, but sensitivity still remains, and additional fabrication requirements can be impractical and costly. As an alternative, the self-stiffened shells are proposed against the imperfection, such as the aster shell, the wavy shell with freeform shapes. Those two shells have corrugated cross-sections rather than circular cross-sections. Our study will focus on the aster and the wavy shell. For designing the wavy shell, the optimization technique do need to be used. The wavy cross-section is defined by control points. A non-uniform rational B-spline is used to create smooth curve through these control points. To narrow the design space, we use the three geometry constraints. First, we use mirror symmetry and fourfold rotational symmetry about two axes. Thus, we only need to consider the control points in the first quadrant. Second, the control points were equally spaced circumferentially and were only allowed to move in the radial direction. Third, for all the control points, the maximal deviation from circle was same. Thus, the optimization problem for the wavy cylindrical shells can be formulated into how to maximize the ultimate stress. For designing a specified shell within the reasonable computation time, we need to use the optimization algorithm. In this study, we use the particle swarm optimization. It's an algorithm that a swarm consists of individuals which fly through n-dimensional search space. Each particle in the swarm represents a potential solution. Let's look at these equations. The current velocity is updated based on the previous velocity, particle-based position, and global-based position. Then the current position is updated based on the current velocity and the position in the last step. During the optimization design, a fitness function is used to guide the particle in finding the global optimal solution in the swarm. We mainly use MATLAB to generate the coordinates of the control points. Use Rhino to read these coordinates and create a perfect shell shape. Then the shape was imported into Abacus and implement LBA, GMNI, and GMNIA. Then we can get the results, and the position and results were returned to the MATLAB. The PSO algorithm will automatically update the position and the results. After running several runs, The shell shape with the maximal ultimate stress can be determined. We have given 4 candidate options for the symmetry and number of control points. The convergence history of ultimate stress for these 4 candidate options and the key results are presented. We can see that the shell with the 4-fold rotational symmetry and 16 control points has the highest ultimate stress, twice higher than that of the reference cylindrical shells. Also, we investigate the Aster shell. Aster shell is a multi-voltage cylindrical shell with an optimal number of volts. The optimal number of volts was equal to twice the circumferential critical Berkeley mode of the circular cylindrical shell. The depth of the volts is a parameter which needs to be optimized. For simplicity, the Aster cross-sections can be defined as half sine waves, which has a concavity pointing inward. The designed Aster shell has the same dimension with the Vevey shell. We can see from the results that the Vevey amplitude of 14 millimeter and the number of the half sine wave of 18 has the highest ultimate stress and is not very sensitive to imperfections as it has a conduction factor close to unity. After designing the Vevey and the Aster shell, we have done some tests. The tests include microstructure observation, tensile coupon tests, the geometry imperfection measurements, and the axial compression tests. We just talk about the 3 later parts. All the specimens were printed by part bed fusion. It belongs to additively manufacturing. It's an advanced technique which produces an object from a digital model through depositing thin layers of metallic materials. It has many advantages such as the ability to build complex geometry. Most any geometry can be applied and multiple materials can be printed together. The material we use is the stainless CX powder. We have coupons and shell specimens built vertically through PVF. During the PVF process, a layer beam is used to melt the metallic powder at the programmed locations to build a component. Here are the cross-sections of the choosing shells, the real photos for the shell during printing and after finish. For the tensile coupon test, we use the digital image correlation to record the actual strain of the coupons. The stress-strain material response and the key results of the coupon tests are presented. We can see that the PBF stainless steel CX material has a higher 0.2% proof stress and low ductility. Before compression tests, we measured the initial geometry imperfection. The outer surface of the shell was scanned using 3D layer scanner and processed in geometry wrap, then input into Rhino in the form of STL file. In the Rhino, the point cloud can be extracted in any longitudinal line. These points can be best fitted into straight line, and the deviation between the fitted lines and the points can be determined. The largest deviation is taken as a local imperfection amplitude. Typical surface deviation profile of the test specimen show that the initial local imperfection was generally very small. Here are the tests set up for the compression tests. The strain gauges coupled with the LVDTs were used to record the actual strain. Besides, the digital image creation was used to capture the speckle pattern and thus obtain the deformation and the strength. It should be noted that DIC is an effective and stable way to look further inside into the deformation and the strain. Four cameras were used at two faces of the test specimens to capture the speckle pattern. After test, we got the deformed shape of these test shell specimens. We can see that the circular cylindrical shell filled by checkerboard local buckling with 7 circumferential waves. The other shell deformed in an asymmetry mode with outward bulging. There was no visible local buckles observed near the peak load. But after testing, localized buckles were seen in the traps of the corrugations. The free-form wavy shell also showed an asymmetry deformation mode and filled by local buckling in the traps of the corrugation. The buckling of the circular cylindrical shell occurred suddenly, with a loud snap and a sudden drop of the applied load. The two corrugated shells, on the other hand, showed a more gentle wear. The aster and wavy shell fared at a low level beyond the plastic load, while the failure of the circular cylindrical shell occurred below this load level. From the load versus end shortening curve, we can see that the two techniques are identical to measure the end shortenings of the specimens. The aster and the wavy shell had a 33% and 46% increase, respectively, in their failure stress over that of the circular cylindrical shell. This increase in failure stress is lower than the expected 200% value. This is attributed to the measured imperfection amplitude of the circular cylindrical shell being lower than the assumed value in the prediction. Thus, the test peak load for the circular shell was higher than the predicted. Finally, we have done the numerical modeling to adjust the FE prediction. The scanned geometry of the outer surface was imported into AVCUS, and GMNIA was conducted. The measured thickness and the material response was used in the simulation. The deformed shapes, peak loads, and deformation at peak loads obtained from the simulation showed a good agreement with the tests. Thus, we can conclude that the investigated corrugated cylindrical shells are found to be imperfection insensitive and found to have a higher loading capacity than the reference circular cylindrical shell through tests and FE simulation. The algorithm particle swarm optimization was used to design the free-form wavy cylindrical shells. In the test, advanced testing technique, 3D layer scanner, and the digital image creation has been featured. That's all for my presentation. Thank you.